In this lesson, we will discuss the key subsystems in an autonomous vehicle. The main subsystems of autonomous vehicles are perception, prediction, planning, decision-making, and control. These subsystems are interdependent and collaborate through a robust network to provide a safe and reliable operation of the vehicle. Let's discuss each subsystem briefly. The perception subsystem is known as the eyes and ears of the vehicle. It uses cameras, sensors, and sensor fusion to gather information about its surroundings. The cameras are used to constantly capture high-resolution visual data, like traffic lights, lane markings, pedestrians, and other vehicles. Depending on the technology used, the cameras can provide varying field of view and can even capture depth information. However, the quality of the images obtained highly depends on the environment in which they are taken, such as lighting conditions, shadows, or even the weather. As stated earlier, the perception subsystem also uses sensors. The most common are as follows. The light detection and ranging or LiDAR. This type sensor uses lasers to create a 3D map of the surroundings with high precision, essential for understanding object shapes and distances. Radar. It emits radio waves to detect objects even in low visibility conditions like fog or darkness, good for identifying moving objects. We also have ultrasonic sensors, which are short-range sensors used for low speed and close proximity detection for parking maneuvers and avoiding obstacles. Next is the inertial measurement unit sensor, which is crucial in navigation. Its uses such as gyroscopes and accelerometers tracks the vehicle's movements and orientation. Finally, the tire pressure monitor systems, or TPMS, is a set of sensors located on the vehicle's wheels to provide information about the air pressure in the tires. As a result, these vehicles can provide better fuel efficiency and longer tire life. In addition to these sensors, the perception subsystem also uses a software component known as sensor fusion. This software combines the data from all the sensors into a unified understanding of the vehicle's surroundings, creating a detailed picture for the prediction stage. For example, acquiring data from multiple sources often results in redundancy from different sensors, making the system less susceptible to individual sensor limitations, failures, or adverse conditions like bad weather. There are three types of fusion algorithms. Early fusion algorithms aggregate the raw sensor data prior to any processing, while the late fusion only combine output from each sensor after they process their raw data individually. As a result, the early fusion approach is more computationally expensive but provides a best interpretation of the vehicle's environment. The fusion, on the other hand, is known to miss key details but is more computationally efficient. The third approach, known as mid-level fusion, fuses preprocessed data like features or object detections from individual sensors. Thus, it offers a good balance between information richness and computational efficiency. Regardless of the algorithm used, fusion technology requires synchronization among the fusion, and the communication between the various components can be vulnerable to cybersecurity threats. The prediction subsystem relies on the details of the environment generated by the perception stage to identify obstacles, classify any perceived objects, other nearby vehicles or pedestrians in order to predict their future and imminent behaviors. The planning and decision-making are considered the brain of the autonomous vehicle. It uses artificial intelligence and machine learning to analyze the perceived environment, traffic rules, and determine the best course of action based on its own goals, such as reaching a destination. It considers factors such as obstacles, traffic signals, and the optimal routes. In addition, the planning subsystem heavily relies on the localization algorithms that tell where the vehicle is located. The localization focuses on knowing the precise location of the car. This information is crucial in path and route planning and trajectory generation. The advantages of vehicle localization include safe navigation and integration with infrastructure. For example, the exact positioning of a vehicle is crucial for lane positioning and following, planning safe maneuvers, following traffic rules, and avoiding collisions, and communication with vehicle-to-everything infrastructure. To achieve this goal, Localization uses the following technologies. Global Navigation Satellite System. This is analogous to GPS. It allows to receive signals from satellites to determine the vehicle's approximate position. GNSS is unable to provide enough information by itself for safe autonomous driving due to limitations such as signal availability and accuracy. Correction services. Advanced systems rely on correction services that refine the raw GNSS data, improving accuracy down to centimeter level in some cases. These services can be ground-based, satellite-based, or a combination of both. Inertial measurement unit. This onboard sensor measures the vehicle's motion, acceleration, and rotation in real time, bridging gaps when GNSS signals are weak or unavailable. Map matching. High-definition maps with precise lane markings, lane boundaries, and other details are used to compare the vehicle's position with the map, further increasing accuracy and enabling lane-level localization. Sensor fusion. Similar to perception, data from other sensors like LiDAR and cameras can be incorporated to confirm landmarks or identify the vehicle's position relative to visible features, contributing to a more robust understanding of its location. Once the plan is set, the control subsystem translates it into action. The control subsystem relies on complex algorithms that translate high-level decisions into low-level control commands. To ensure smooth and safe operation as well as passenger comfort, the control algorithm considers factors such as vehicle dynamics, road conditions, traffic rules. Here are the key functionalities of the control subsystem. Hardware integration. The control subsystem works in close coordination with the vehicle's onboard computer and electronic control units, also known as ECUs. These components communicate seamlessly to translate commands into tangible actions. Command generation. Once the planning subsystem determines the optimal path and the perception subsystem provides real-time information about the environment, the control subsystem takes over. It processes this data and generates specific commands for the vehicle's actuators, steering, brakes, throttle. Actuator control. The control subsystem sends precise instructions to the actuators, dictating how much to turn the steering wheel, how hard to apply the brakes, and how much power to deliver through the throttle. This controls the vehicle's movement, maintaining its position on the planned path while adhering to traffic regulations and safety considerations. Feedback loop. The control subsystem doesn't operate in isolation. It constantly receives feedback from various sensors, wheel encoders, LiDAR, cameras, to monitor the vehicle's actual behavior. This feedback loop allows the control system to make real-time adjustments and ensure the vehicle follows the planned path accurately. Fault tolerance. The control subsystem is designed to be robust and handle unexpected situations. It should be able to detect and compensate for minor errors or sensor malfunctions. In some cases, it might even trigger emergency maneuvers to bring the vehicle to a safe stop if a critical system failure occurs. There are other key subsystems in autonomous vehicles, notably the communication and the computing resources. Vehicles of the future may talk to each other and to infrastructure using technologies like vehicle-to-everything or V2X to share information and coordinate actions, further enhancing safety and efficiency. Key functions of the communication subsystem include sensor data acquisition. The communication subsystem gathers real-time data from various sensors on the vehicle such as LiDAR, radar, cameras, and ultrasonic sensors about the surrounding environment, including the presence of other vehicles, pedestrians, traffic signals, and lane markings. GNSS integration. The communication subsystem interacts with the GNSS receiver, which provides the vehicle's precise location data using satellites. This information is crucial for navigation, route planning, and maintaining situational awareness. Cellular network connectivity. Cellular networks allow AVs to connect to the cloud and transmit data for various purposes. This data can include sensor readings, diagnostic information, software updates, and real-time traffic data. Cloud connectivity also enables remote monitoring and control of AVs by operators. Internal communication network. The communication subsystem facilitates communication between different onboard components of the autonomous vehicle. This includes the exchange of data between the control units, ECUs, electronic control units, and other processing units within the vehicle. Vehicle to everything V2X communication capability. V2X communication allows AVs to exchange data with other vehicles, V2V, infrastructure, V2I, and pedestrians, V2P. This data exchange can include information like location, speed, direction, and potential hazards. V2X communication enables cooperative maneuvers, improves traffic flow, and enhances safety by allowing vehicles to anticipate the actions of others. The computing components provide support for other subsystems by processing data and generating necessary outputs. It includes both hardware and software resources. Powerful processors and specialized hardware are needed to crunch the massive amount of data generated by sensors, run complex algorithms, and make real-time decisions for safe navigation. The software component runs the algorithms for each subsystem and ensuring smooth communication and coordination.